Imagine this sort of cosmic graveyard, right? Where stars end their lives and become these quiet, dense things called white dwarfs. But what if, even there, they get a second chance, an explosive one? Okay, so that's what we're going to dig into today. Double white dwarf mergers. And this isn't just, cosmic fender benders. It's about gravitational waves, really massive star remnants, and even where some of the universe's biggest bangs type Ia supernovae come from. Think of this as your shortcut to some seriously cool, cutting-edge astrophysics.
Yeah, and what's really exciting now is how we can actually see evidence for this stuff, especially with the Gaia mission from ESA. These theories about mergers have been around for a while, but Gaia's data is letting us finally confirm them. We've looked at everything from the basic physics of white dwarfs to the absolute latest Gaia results. It's a cool story of observations catching up.
Okay, so let's set the scene properly. What exactly is a white dwarf? I know our listeners track this stuff, but a quick refresher. They're pretty much the end of the line for most stars, right? Like 97% of them. Stars that start out less than 9 times the sun's mass or so.
Exactly. They come from stars, kind of like our sun, that fuse helium into carbon and oxygen. Then, after their giant phase, they puff off their outer layers, and what's left is that super dense core. Mostly carbon and oxygen. We're not talking the real heavyweights here. Those end up as neutron stars or black holes after supernova. This is the much more common endpoint.
Right. So super dense. What kind of mass are we talking about? Is there like a maximal weight?
Yeah, typically they're between maybe zero point 0.2 and 1.3 times the mass of the sun. Most are around zero point 0.6 solar masses. And this is absolutely key, there is a limit, a theoretical maximum for one that's not spinning. It's called the Chandrasekhar limit. That's about 1.44 solar masses. Think of it like a cosmic weight limit.
Okay, the Chandrasekhar limit. Why is that number, 1.44, so important? What happens if a white dwarf gets heavier than that?
It's critical because that's the point where the star can't hold itself up anymore. It's supported by something called electron degeneracy pressure, basically, electrons resisting being squeezed too close together. But if a carbon-oxygen white dwarf gets too much mass, often by stealing it from a neighbor star, it goes over that limit. It can't fight gravity anymore. And boom, type Ia supernova, a really spectacular explosion.
And besides mass, is there anything else about white dwarfs that's important when they merge, like magnetic fields?
Oh yeah, magnetic fields are definitely relevant. We can measure them by looking at how light splits in the field that's Zeeman splitting. And the fields can range from pretty weak, like zero point 0.2 Tesla, up to, well, 100,000 Tesla, which is huge. And get this, about 10% of the ones we see on their own have really strong fields, over 100 Tesla. That turns out to be a clue later on.
Okay, so here's where it gets really interesting, I think. These white dwarfs aren't always alone. Sometimes you get two of them orbiting each other, right? Double white dwarf binaries. Basically the final stage for a lot of binary star systems. If nothing disrupts them earlier, you end up with two white dwarfs doing this sort of cosmic dance.
And these systems are incredibly important. They are the main source of low-frequency gravitational waves, ripples in space-time. Future missions like LISA and Tianqin are being designed specifically to hunt for those waves coming from these pairs. What's amazing is that the only thing driving their evolution closer together is losing energy through those gravitational waves. It's a guaranteed inward spiral. Actually, Gaia data has already helped flag about 400 potential short-period pairs. They're just spiraling in, waiting to merge.
And this connects back to the supernovae we talked about. Type Ia. These double white dwarfs could be the starting point for some of them.
That's the idea, yeah. It's been considered for decades by researchers like Webbing back in '84 and others more recently, and theory predicts that loads of these pairs should merge within the age of the universe. We should see the results. Often, the merger probably just creates one bigger white dwarf. But here's a wild thought. This means maybe 10–30% of all white dwarfs, and maybe even up to half of the really massive ones, aren't single stars at all. They're merger products, which could mean we're getting the ages wrong for some massive white dwarfs because we didn't account for that merger history.
Wow. Okay, so if the theory says these mergers happen and create these unique objects, how do astronomers actually go out and find the evidence, find the proof?
Well, there were sort of two main ways people tried. The first was, the simple approach, just count them, look for too many heavy white dwarfs compared to what single-star evolution predicts. But that turned out to be really difficult. You get big errors from uncertainties in how a star's starting mass relates to its final white dwarf mass, and just not having complete enough catalogs of stars.
Right. The counting was tricky. What was the other approach?
The other way, which got really exciting, was looking for kinematic signatures, basically how these things move. The idea is this. If a massive white dwarf formed from a merger, it likely took longer because of the whole binary evolution dance. So it should be older, on average, than a massive white dwarf from a single star. And in our galaxy, older things tend to move faster, more randomly, they have a higher velocity dispersion. So the prediction was merged white dwarfs, being older and massive, should be moving faster than their single-star counterparts.
But finding that signal was tough before Gaia, wasn't it? I remember reading about studies using older surveys.
Exactly. There was a study around 2012 using Sloan and Palomar Green data. They looked for this velocity trend. They actually found the opposite velocity dispersion seemed to decrease with mass, which pointed towards most high-mass white dwarfs coming from single stars. But the big caveat was, as they put it, the paucity of good white dwarf kinematics, just not enough good motion data.
And then Gaia.
And then Gaia, yeah, it completely changed everything. Gaia DR2 suddenly gave us precise movements for like 260,000 white dwarf candidates. And then EDR3 pushed that over 1 million systems, including finding 1,400 double white dwarf binaries directly. It was a revolution for this field.
So with Gaia's data, people could finally test that kinematic idea properly.
Precisely. A team led by Cheng started looking right away with Gaia DR2 in 2019. They were actually looking at something else, this weird bump in the number of white dwarfs at a specific mass, the Q branch, related to when their cores start to crystallize, like cosmic diamonds forming. But as part of that, they looked at the kinematics, and they found about 22% of the white dwarfs in their mass range looked like merger products based on how they moved.
Just as a byproduct of looking for something else. That's cool.
Yeah. So then in 2020, they expanded it big time, used a sample 40 times larger, over 1,000 high-mass white dwarfs. And looking at their transverse velocities, how fast they move across the sky, they again estimated about 20% were merger products, really consistent.
Okay, 20%. That sounds significant. What did that number mean for, like, the whole galaxy?
It was huge. Because with that percentage and the large sample, they could calculate the rate at which these mergers happen in the Milky Way. Their number was way more accurate, like 2-3 times better than previous guesses, and crucially, that rate. It was high enough to support the idea that double white dwarf mergers could actually account for a significant fraction of all type Ia supernovae, specifically through a channel sometimes called the D6 mechanism.
D6. Okay, what's the D6 stand for? Sounds dramatic.
It does. It's dynamically driven double degenerate double detonation.
Whoa, okay, break that down.
Right. So double degenerate just means 2 white dwarfs. Dynamically driven means the merger process itself is key. And double detonation, the idea is maybe the initial merger triggers a smaller explosion on the surface, which then triggers a much bigger one that detonates the whole accreting white dwarf.
And the other white dwarf.
Yeah.
The donor.
Ah, that's the other cool part of D6. In that scenario, the donor might actually survive the explosion but get kicked out at incredible speed, like its old orbital speed.
So flung out as a hypervelocity star.
A runaway.
Exactly, a hypervelocity white dwarf. And we've actually found candidates for this. Back in 2018, Shen and colleagues used Gaia DR2 to find 3 white dwarfs zipping away from the galactic center at over 1,000 kilometers per second. Insane speeds.
1,000 kilometers a second. Wow.
Yeah, and follow-up work with even better Gaia data in 2021 confirmed them and helped pin down the properties of these ejected donors. It's pretty direct evidence for that D6 channel happening.
That's amazing. So we have the statistics and we have these direct runaway examples. Are people finding other individual merger products too, like ones that didn't run away? Yes, definitely. There's another approach. Searching existing white dwarf databases, but using Gaia's precise data to look for weirdos. Killick and collaborators did this in 2021 and 2023, looking at white dwarfs within about 100 parsecs, so our local neighborhood. They focused on the real heavyweights, the ultramassive ones, over 1.3 solar masses. Out of 25 they looked at, they concluded at least 8 were probably merger products. They stood out because of, again, high velocities or strong magnetic fields or spinning really fast, all things you might expect from a merger. It's like finding cosmic fingerprints.
Okay, so kinematics, runaways, individual weirdos. Any other lines of evidence?
There's another really neat statistical one. Fleury and colleagues used Gaia EDR3 data in 2022. They looked at white dwarfs in a certain mass range, 0.95 to 1.25 solar masses, within 200 parsecs. And they compared the distribution of their cooling ages, how long they've been cooling down, to the star formation history of the galaxy, which Gaia also helped measure.
Okay, comparing how old the white dwarfs seem to be with how many stars should have formed back then.
Pretty much. And what they found was really telling. For the slightly lower mass ones in their sample, 0.95 to 1.15 solar masses, the ages match the star formation history just fine, consistent with single star evolution. But for the really massive ones, 1.15 to 1.25 solar masses, the age distribution looked totally different. It was much, much better explained if you assumed that a big chunk, like 40 to 50% of those white dwarfs, actually came from double white dwarf mergers over the last 4 billion years or so.
40 to 50%. That's
It's
huge. So half of the most massive nearby white dwarfs might be merger products.
That's what their analysis suggests, yeah. It's another strong piece of evidence pointing to mergers being really common for creating these high-mass objects. And it all ties together nicely with theoretical work, too. Other recent studies show the merger process itself tends to naturally create white dwarfs that are highly magnetic, spinning uniformly, and often born very close to that Chandrasekhar mass limit. Plus, there are now incredibly detailed models of how these merged objects should cool down over billions of years, accounting for all sorts of complex physics inside them, like crystallization and element settling. These sophisticated models are crucial for interpreting the kind of precise data Gaia gives us.
Wow. So putting it all together, the picture seems much clearer now, thanks to Gaia, doesn't it?
Mhm.
We're not just drawing diagrams anymore. We're actually seeing the impact of these double white dwarf mergers. We see their kinematic signatures, we see the runaways, we find individual massive objects that look like mergers, and even their age distributions point towards it. It confirms they make these ultramassive white dwarfs and potentially are a major source of those vital type Ia supernovae. It feels like we've peeled back a layer on stellar evolution.
Absolutely. And it leaves you with this really intriguing thought, doesn't it? If so many of these apparently single massive white dwarfs are actually the ghosts of past mergers, well, what does that really tell us about how stars live and die, especially in binaries? It could change how we map stellar populations, how we estimate the ages of different parts of our galaxy, realizing that some of the oldest looking things might have had this incredibly dynamic, violent merger in their past. It just shows there are still so many stories hidden in the stars, and Gaia is really helping us read them.